Our first talk is going to, well, I guess our only talk this afternoon will be Zach Walsh, who's going to tell us about the foundation of a generalized parallel connection.
Okay, thank you, Diane, and thank you to the organizers for the opportunity to speak today. So, yeah, before I start, I just have a confession to make, which is that until this morning, I thought my talk was supposed to be 30 minutes instead of an hour. So since then, I added a few slides, but I'm saying this because I want to encourage you to ask questions if anything is unclear. I should have some time to answer questions during the talk. Okay, so yeah, so I'll be talking about some joint work with Matt and Oliver and Matt's former student Tianyi. And yeah, I don't want to assume any knowledge about these words in the title, so I'll spend most of the time telling you what is the foundation of a matroid, giving some background, and what is a generalized parallel connection of matroid, the gluing operator. And then at the end, I'll tell you some things that we proved relating these two concepts. Okay, so we'll start with matroid foundations. So the foundation of a matroid encodes its representations over fields and more general objects called pastures. So to start with, I just want to give a maybe slightly different perspective on matroid representations. Okay, so here's kind of the traditional perspective. You have some matroid like this one over here with ground set E and basis B, just a rank 2 matroid. And a representation over a field F or a realization is a matrix whose column set is E and whose bases of the column space are E. Okay, but it turns out you don't actually need the matrix. So if I just take this matrix and I write down this function, if I write down the function that maps an R tuple of the columns to its determinant, the determinant of that submatrix, then this function satisfies 3 natural conditions. Okay? It maps an R tuple to something non-zero if and only if that R tuple corresponds to a basis of the matroid. This function respects the signs of permutations of the columns, and it satisfies the 3-term Blucher relations down here. Okay, so the determinant function satisfies these properties. But my point here is that conversely, if I just have a function delta that satisfies these 3 conditions, then I can construct a matrix that represents the matroid. This is probably obvious to some people in here. It's not obvious to me personally, but you can prove it. Yeah, so you don't need the matrix. And okay, what's the point of this? Well, the point is that with this definition, we're not really using addition in the field very much. Right? We're only adding 3 terms at a time to make sure we satisfy these 3-term flip relations. Okay, so the idea is that we can actually study matroid representations over objects that are more general than fields if we just relax addition and just study this set of triples. So triples that sum to 0. Okay, and yeah, this has been formalized by Matt and Oliver, and these more general objects are called pastures. So before we go through this definition, I should mention, I mean, this builds on a lot of previous work that I won't really talk about very much. So pastures are specific examples of tracts, which were introduced by Matt and Nathan Bowler, and they're also specific examples of ordered blueprints of Oliver. Okay, so I'm kind of ignoring some background. We're just going to focus on these objects in this talk, these pastures. Okay, so here's a definition. So it's a multiplicative monoid with 0. What this means is that there's just an element called 0 that is multiplicatively absorbing. And this set, if I take away 0, it's just an abelian group. Okay. But I take this set together with a set of its triples. Okay. So here this n stands for null. This is the null set. And this set of triples just is going to satisfy 4 properties that is satisfied by addition in fields. Okay. So the first property, if I have a triple XYZ in my null set, then every permutation is also in the null set because addition over fields is abelian. Okay. And if I have a triple in the null set, I can scale it and get another triple in the null set. And 0 is unique in this sense here. X00 is in my null set if and only if X is the 0 element. And there's also a unique element epsilon that behaves like -1 in the following sense. 1 epsilon 0 is in the null set. Yeah, 1 epsilon 0 is in the null set, and epsilon is unique with this property. Okay, so you can think of epsilon as behaving like -1. Okay, yeah, and the point here, well, there's a few points here, but this generalizes fields. So if I have any field, I can think of it as a pasture where XYZ is in the null set if and only if those 3 elements sum to 0 over the field. Okay. But kind of the big deal here is that every partial field is also a pasture and every hyperfield is a pasture. And there's a long history of studying matroids over partial fields and matroids over hyperfields. And these are now unified by studying matroids over pastures. And we'll see some examples in the next few slides. Yeah.
For the third and fourth condition, do we also want to have like the permutation of the location? So like, should we have the same condition as the third one for Y in the second spot and then 0, Y, 0?
Yeah, I mean, I guess.
Oh, thank you.
Yeah, for these ones, I guess I'm just fixing X to be in the first spot.
Totally makes sense. Thanks.
What are partial fields and hyperfields?
Yeah, we'll see some examples and yeah, good question. Yeah, I don't expect anyone to know what these are. Yeah. Okay. Anything else before we move on? Okay. Yeah, okay. So here's some examples that are not fields, and these are very important examples, and we'll see why shortly. Okay, so these are just some very basic pastures. So here, the set is just 0, 1, -1 with the multiplication that you would expect. And my triples in the null set are just 0, 0, 0, which has to be in there. And then permutations of 1, -1, 0. Okay, I mean, yeah, and this is a pasture. It satisfies those 4 properties from the last slide. And this one is called the regular partial field. Okay. Yeah, so what does this mean? So what this means roughly is that 1 -1 equals 0. So I know how to add 1 and -1, but I don't know how to add, for example, 1 + 1. Because there's no triple. There's no triple of this form. Okay, so addition is only partially defined here. Okay, a partial binary operation, and that's what a partial field is. Okay, so this is just one example of a partial field. Okay. Okay, yeah, and this one is very restrictive because there's really only one non-trivial thing in my null set. I only know how to add 1 and -1 and nothing else. It's very restrictive. Okay, so here's one that's a little bit less restrictive. So my underlying set is still 0, 1, -1. I still have the multiplication that you would expect. But now I'm going to put in some more triples. So now I have all permutations of these 3 these three triples here in my null set. Okay, so what's happening here, I'm basically putting in any triple where I have elements with different signs, one, and minus one. Okay. And yeah, this set here with these, with this set of triples is a pasture, satisfies the four properties from the last slide. And this is called the sign hyperfield, the hyperfield of signs.
What do you mean by is here? Like when you say there is the sign hyperfield?
Oh yeah, I'm not sure. I mean, is isomorphic to the sign hyperfield? I mean,
I think maybe, well, I had the same question for the class. I mean, like you're giving a general way to reconstruct the addition, the hyperfield addition from this data.
Yeah. So okay, yeah. So what's happening here is okay. So if I look at these triples, so this first one is saying like 1 minus 1 equals 0. This one, if I permute it, is saying 1 minus 1 equals minus 1. And this one is saying 1 minus 1 equals 1.
Did you use your epsilon there to change the sign on the one side? How did that work?
For this last one here?
Yeah, last two.
Yeah, so okay, so all I'm doing is I'm saying, I maybe just like skipping a step. So really what this is saying is like 1 minus 1 minus 1 equals 0. And we can think of that as like 1 minus 1 equals 1. I mean, I'm writing this in quotations because there is no addition, there is no subtraction, there's only triples, but yeah, this is why this is a hyperfield, because the sum of 1 and minus 1 is set, right? It could be 0, it could be minus 1, or it could be 1, right? So this is what my understanding of what a hyperfield is that the sum of two elements could be a set. It doesn't have to be a specific element. Okay, and then one more kind of fundamental pasture is this Krasner hyperfield here. So this one's even simpler. The elements are just 0 and 1, and I'm actually going to put in every triple that I'm allowed to while satisfying the pasture axioms. Okay, so permutations of 1, 1, 0 and 1, 1, 1. So here we have epsilon is 1. So 1 and minus 1 are equal over this pasture. Yeah, and okay. This set here with these triples satisfies the pasture axiom. This is a pasture. It's also a hyperfield known as the Krasner hyperfield. Okay. Okay, maybe I'll pause here. So are there other questions about this? Okay. Okay. So yeah, now we have pastures. We need to say, I need to say how you represent a matroid over a pasture, and yeah, this just is the same definition as the first slide. Okay, so given a pasture P, a P representation of a rank R matroid with ground set E is just a function delta from R tuples of the ground set to the pasture that satisfies these three properties. Same as the first slide. The only difference here is that I don't have addition. So instead of writing the three-term Kluger relations with addition, I just say that triples of this form here must be in the null set. Okay.
What is this epsilon here?
Yeah, so this epsilon is like it behaves like -1. Yeah.
Oh,
Yeah.
Is that how you define like sign of a permutation?
Yes. Yeah. Yep. Okay. Yeah. And, okay, I should mention that, if you have a matrix representing a matroid, you can do row scaling, row operations, column scaling, and still have the same associated matroid. You can also do those operations directly from this function here. Yeah, I should mention.
Sign then give you epsilon. Like, how does this sign here work?
Yeah, so this is either going to be a 1 or an epsilon.
Okay.
Yeah. I should mention before I forget that this is called a Grassmann-Fluker function in the current terminology.
Is epsilon times epsilon equal to 1?
Yes, yeah. Yep. Okay. Let's see, what else do I want to say here? Yeah, so yeah, I wanted to say you can also do, you can model scaling directly from this definition. So if I just scale this entire function by some element of the pasture, it will still satisfy these three conditions here. Okay. I can also just pick some specific element like E2, and I can just scale all the outputs of tuples that contain E2. And that behaves like column scaling in the determinant function for a matrix.
Does such function give you also one-click relation?
Sorry.
Does such function delta give you also one-click relations, analog of long-click relations?
Yeah, so okay, yeah, so the point here is that, yeah, over pastures, the higher order Fluker relations don't make sense because I'm only allowed to add 3 terms at once. Yeah, if that's what you're asking. Yeah. So that, I mean, yeah, okay. There are these, I don't want to get too off track here, but there's these more general objects called tracts, which generalize pastures, and then you can have you can also have a Grassmann-Fluker function that satisfies higher order Fluker relations, and that's called a strong Grassmann-Fluker function. This would be a weak Grassmann-Fluker function. But for this talk, since we're just focusing on pastures, this is all we can really do. Okay. Okay. Yeah. So why is this a good definition? There's a few reasons, but the main one is that now we can study existing important classes of matroids as matroids that are representable over a specific pasture. Okay. So matroids that are representable over the regular partial field are exactly regular matroids. So equivalently, these are matroids that have a representation over every field. It's fundamental class of matroids. Matroids that are representable over the sign hyperfield are orientable. Representations of a matroid over the tropical hyperfield T are valuations of the matroid. And yeah, one other nice thing about studying matroids over pastures is that every matroid is representable over some pasture, namely the Krasner hyperfield. You just have, in this function, you just map every basis to the element 1 and every non-basis to the element 0. Okay. Yeah.
Can you compute the orientation classes of a matroid in terms of its representations over S?
Yeah. So I believe that reorientation classes of the matroid correspond with rescaling classes of representations over the sign hyperfield. Yeah.
Maybe related. What's the bijection between the regular matroids and representations of plus minus?
Oh yeah. So okay. So if you have a regular matroid, then I believe the definition is that it's representable by a totally unimodular matrix. So every determinant is 0, 1, or -1, and that gives you the map. That gives you this map into the regular partial field. whose elements are just 0, 1,
Which
and minus.
turns out to be a bijection.
Yeah, so, yeah, the other direction, if you have, yeah, that's not obvious. If you have a function like this that maps into the regular partial field, yeah, then you can construct a totally unimodular matrix that represents your matroid. Yeah, and that's not obvious to me, but I imagine it's not too hard to prove. Okay, yeah, I mean, this is probably the main concept from the talk here, matroids over pastures. So maybe I'll pause here for another second. Is any other questions?
If you have a weak Grassmann-Fluker function, then it gives you a matroid. Yeah.
Well, yeah. So this
The last part is also goes two-way. The last bullet.
A Grassmann-Fluker function is with respect to a specific matroid.
So I'm saying that taking number one as definition of a base.
Oh, yeah. So this, yeah.
No.
As I understood that question, I'd give the answer no.
That
is to say, you can have a function from R tuples of E to even to a field whose support is not a matroid, but obeys conditions 2 and 3.
Okay, yeah, thanks.
There's one rank 3 on 6 elements.
Okay.
What is exactly the difference between strong and weak matroids, or strong and weak Grassmann-Fluker functions? Is that strong means you satisfy all the relations like this, including the 4-term, 5-term, etc. And that does imply that you have a matroid underlying it, but if you only ask for a 3-term, it's
Okay.
you have to assume at the beginning that the support is already a matroid.
Okay, yeah, thanks.
Just one more addition that Zach mentions this basically already, but there's a magical fact that if your support is a matroid, then the 3-term Fluker relations are enough to determine what in the cross model. I mean, then it's a case if you're over a field.
Okay. Okay, yeah. So this is the matroids over pastures. It's a nice. The point is, it's a nice theory that generalizes a lot of existing research in matroid theory. Okay. So yeah. So now I'll just mention a couple other nice things about working with matroids over pastures. So the next thing is that the category of pastures has some very useful properties for working with matroids. So here the morphism between two pastures is just a function that preserves multiplication, and it preserves these triples in the null set. Okay. Okay. So what are some nice properties of this category? So it has initial object as the regular partial field. This has a morphism to every other pasture. It has final object K, the Krasner hyperfield. Every pasture has a morphism to the Krasner hyperfield. And it also has products and co-products. Okay. So for example, the product of the 2-element field and the 3-element field is the regular partial field. Okay. So I'm pretty new to category theory. I should say this is not my background. So the way I understand this is that this regular partial field is like the most general. It's the most general pasture that has morphisms to F2 and F3. Okay, and since this is the initial object, it's actually unique. Okay, and the product of the 2-element field and the sign hyperfield is also the regular partial field. And the co-product of F2 and F3 is the Krasner hyperfield. This is the only pasture that has morphisms from F2 and F3. Okay, Yeah, so I should mention, I mean, so these are just kind of computations. So you can actually do these computations in Macaulay 2 if you want. Pastures have been implemented in Macaulay 2. But these computations actually prove well-known results in matroid theory. So this one proves Tutt's theorem that every matroid that is binary and ternary is also regular. Okay? And that just follows from the definition of product here. Okay. And this one proves a theorem of Bland and Las Vernias that every matroid that is binary and orientable is also regular. Okay, so this yeah, I mean, that's just a really nice consequence of having products here.
What does the coproduct thing say? Are you guys solved?
Yeah, so actually we're going to focus on this one. This will kind of play an important role in this. Oh, yeah. Okay. Okay, so now we can finally get to matroid foundations. So the first word in the title. So, okay, I'm gonna explain this with this theorem here. Okay, so Matt and Oliver have this theorem that for every matroid M, the functor taking a pasture P, the set of rescaling classes of P representations of M is representable by a specific pasture F of M, and this is the foundation of M. Okay, so every matroid has a canonical associated pasture called its foundation. Okay, and yeah, it controls representations of the matroid over any pasture, right? So representations over a field, reorientation classes, if it's orientable. Okay. Yeah, so in particular, for any pasture P, the morphisms from the foundation to that pasture are in one-to-one correspondence with rescaling classes of P representations of M. So if you want to understand representations of a matroid over anything, any field, partial field, hyperfield, you should know its foundation, right? That'll tell you all the information you need. Okay. Yeah, and we'll look at some examples in a second. I just want to say that this ties in really nicely with a lot of existing algebraic invariants in matroid theory. So the underlying multiplicative group of the foundation of a matroid is the inner Tutt group of the matroid. If you know what that is, if not, that doesn't matter for this talk. This was studied by Dress and Benzel. And if your foundation happens to be a partial field, then it is the universal partial field of the matroid, which was introduced by Pendapping and Dunswan. Yeah, so my point is that there's a lot of evidence that foundations are very natural objects. Yeah, so just some examples. So a lot of times, foundations behave how you would expect. So if I take any graph G, the foundation of the graphic matroid of G is the regular partial field. And this is just because graphic matroids are regular. Yeah, so this is true for any regular matroid. The foundation is the regular partial field. Another example that maybe matches your intuition is that the foundation of a projective geometry over a field of order Q is just that field. Okay. Okay. And yeah, one thing I think is really cool is that the foundation of the Walsh matroid is actually an interesting pasture. Okay, it's not the Krasner hyperfield, and yeah, I think this is cool because the Walsh matroid is not representable over any field or partial field. It's not algebraic. It's kind of hard to to understand, but this gives kind of a new approach to maybe shedding some new light on what this matroid, on properties of this matroid. Yeah.
Is it true that the foundation of a random matroid is K or a large?
Oh, yeah, I don't know. I think that's a really good question. Yeah.
What would be an example of a matrix's foundation?
Yeah, so, okay, so this is kind of, yeah, we'll talk about this more in a minute, but the direct sum of the Fano plane and like a ternary plane, projective plane, foundation. Yeah, foundation. The foundation of this direct sum here is the Krasner hyperfield. Yeah, and we'll see why this is true in a minute. Essentially, it's because this foundation is the binary field. This foundation is the ternary field. So you need some pasture that has morphisms from both those fields, and the only option is the Krasner hyperfield.
We haven't been bold enough to conjecture that in writing, but I'll say out loud that conjecture that a random matroid has foundation equal to the Krasner hyperfield.
At least in algebra.
I'm going to suggest that the quotes from co-authors come after the talk.
I would guess that if M prime is a minor of M, you get some map from the foundation. I think of M to M prime, let me ask you, which way does it go? What's the statement?
Yes, yeah, you're right. So this behaves well with minors. So if a matroid is representable over a pasture, then so is every one of its minors. Yeah, I won't really talk about minors too much in this talk, though. But yeah, actually, that reminds me of something I wanted to mention. So yeah, so the foundation of a matroid has this universal property here with respect to representations, but you can also, I mean, you can explicitly write down the foundation of a matroid from its information, like its bases or its hyperplanes or its small minors, actually. Yeah, that won't really play a role in this talk, but you can ask Matt or Oliver how that works. Yeah. Okay, yeah, so these are
Just one interesting.
I mean, yeah, I am skipping a lot of interesting things here. Yeah. But yeah, I mean, this is the first, it's the first day of the conference, so you have lots of opportunities to ask us questions about these foundations. Okay, yeah. But yeah, this is all that we really need about foundations for this talk here. Okay. Okay, yeah, and I think this is the first part of the talk. So these are matroid foundations. Next, I'll change gears and I'll say something about this construction, this generalized parallel connection.
I've got another question.
Yeah.
Is it possible for any pasture to construct a matroid so that you get that pasture as a foundation of the matroid?
Yeah, that's a great question. The answer is no. This has been studied quite a bit by Matt and Oliver. I think that's a question that I think they're very interested in. So we should talk to them later. Yeah.
But won't say anything about it.
Yeah. Yeah. Yeah, I mean, there's just a lot of really interesting questions about foundations. Okay. Yeah. So okay, one interesting question that that we focused on here was how do foundations behave with respect to fundamental matroid operations, and in particular, we focused on gluing operations, and we focused on this very general one, this generalized parallel connection. So yeah, I'll tell you what this is, and then I'll tell you why this is a good thing to study. Okay, so this was introduced by Berlowski. So here's how it works. So let's say we have two matroids, M1 and M2. Their ground sets agree on some common set T, and T satisfies one condition. It is a modular flat of the second matroid. So what this means is that if I take T and any other flat of the matroid, they satisfy the submodular rank inequality with equality. Okay, that's what modular flat means. Okay, then I can construct a new matroid. I can glue these together. I look at this set here. So all sets F whose intersection with M1 or M2 is a flat. So M1 and M2. So it has to be a flat in both matroids. Then this is the set of flats of some new matroid denoted with this expression here. And it's called the generalized parallel connection of M1 and M2 along the set T. Okay, so this, I mean, it's a pretty long definition. What you should probably do is just look at this picture here. So here's just an example. So here, this matroid here, this is M1. It's a rank 3 matroid. These lines are the hyperplanes with at least 3 elements. And this here is another rank 3 matroid M2. Okay, and this set here, so this is just a rank 2 uniform matroid, is T. It's their common intersection. And yeah, this whole matroid here, it's a rank 4 matroid. This is the generalized parallel connection of M1 and M2 along T. So this is kind of like a book with the first page is M1, the second page is M2, and the spine is like T. You have a geometric picture for generalized parallel connection. Yeah.
Is the modular condition kind of visible in a picture like this?
Oh yeah, good question. Yeah. So you can check from the picture that T is a modular flat of this matroid. And for rank 3 matroids, that just means that any hyperplane has to intersect T. Okay. So if I take any hyperplane like and hyperplanes have rank 2 here. Like if I look at the hyperplane spanned by these 2 points, it intersects T right here. And that's true for any hyperplane intersects T. And for rank 3 matroids, that's enough to show that T is a modular flat. Yeah. Okay. Okay, so why did we focus on generalized parallel connection? So this is the same definition. So have to read that again if you don't want to. We focus on generalized parallel connection because it gives us at least 4 fundamental matroid operations as kind of special cases. Okay. So if I do a generalized parallel connection with T as the empty set, right? If my matroids are simple, that's always a flat, and it's a modular flat. And this construction is the same thing as the direct sum of the 2 matroids. So it generalizes direct sum. If my matroids are simple and they agree on just a single element E, that's always a modular flat and actually in both matroids. So I can construct this new matroid here. And this special case is known as the parallel connection of M1 and M2 along E. And this is just a very fundamental operation. It generalizes gluing 2 graphs together along an edge. That's what we're doing here. Yeah, and then a couple others. So if you do this parallel connection and then you delete the common element E, this is called a 2 sum of the matroids M1 and M2. It's also very important. And then one interesting one is if I take my second matroid to be the graphic matroid of K4, the complete graph, and I do this generalized parallel connection along a triangle T, and then delete the triangle. This is a pretty important operation called the delta Y exchange of M along T. And this also generalizes a graph operation.
When M is graphic?
M doesn't have to be graphic. M can be any matroid here, as long as it has a triangle.
I mean, does it have like a picture?
Oh, yeah, yeah. So yeah, when M is graphic, what's happening is that I'm just taking a triangle of the graph. I don't care what the rest of the graph looks like. And I'm just replacing it with a degree 3 vertex. So I delete the edges of the triangle and add a new vertex that is adjacent to the 3 vertices of the triangle. So this is called delta y exchange because triangle looks like delta. It really is. And the degree 3 vertex looks like upside down y. Yeah. Yeah. And yeah, if you do a delta y exchange where M is graphic, you end up with another graphic matroid, which is the graphic matroid of this thing. Yeah. Okay, I'll draw some more pictures for this construction a bit later. Okay. Other questions about this?
So this thing is invertible, the delta y exchange?
Yeah, thank you. Yeah, it is also invertible. So it's invertible via duality. So okay, so yeah, okay, maybe I'll draw a picture now. So what's happening is I have some matroid M with a triangle T. I'm kind of gluing on a copy of K4, which looks like this. Okay, so this is K4. And then I'm deleting the triangle. So I've added 3 new elements to my matroid. These 3 new elements are a triad. They're a triangle in the dual matroid of this thing. So now in the dual matroid, I can do a delta y exchange. And then if I take the dual again, I end up with M. Yeah, thanks. Yeah, okay, I should mention there's a caveat. The thing I said is only true if T is independent in the dual to start with. Otherwise, you can't undo it. Yeah. Okay. Other questions?
So the inverse is not a generalized parallel connection.
It is a generalized parallel connection in the dual, so not in M. Yeah.
So that increases the rank by 1?
Yeah, that's another good question. Yeah, this increases the rank by 1. Yep. Okay. Okay, yeah. So now we know about foundations. We know about generalized parallel connections. So there's a natural question here. Can I write down the foundation of this matroid here in terms of the foundation of M1, M2, and their common restriction T? Right?
What do you mean by FT?
Yeah, so okay. What I mean is the foundation of M1 restricted to T, or M2 restricted to T. So okay. Yeah, and there's a natural guess for what for what this foundation should be. Okay. It should be the relative tensor product of the foundation of M1 and M2 with respect to the foundation of T. Okay. So why should this be the right answer? Basically, just by the definition of this relative tensor product, there is always a morphism in this direction from right to left. And you might hope that this is always an isomorphism. Yeah, but unfortunately it's not. It's not always an isomorphism. And this situation here is a counterexample. Okay. So how do we check this? I mean, we just use Macaulay too. Okay, so yeah, I think we don't fully understand what's happening here. At least I don't. But we check this in Macaulay too. You know, foundations have been implemented. You can just input this matroid, compute its foundation. You can just compute this relative tensor product, and these 2 pastures are just not isomorphic.
Are they never isomorphic, sometimes isomorphic?
They are sometimes isomorphic, yeah, and yeah, okay, well, I'll show you what we proved. So
Sorry, before we go, is
yeah.
it possible to say it's probably obvious, but what's the map from FM1 to FT?
Yeah, so that's just yeah, that's the map you get from a minor, matroid minor. So T is a minor of M1 and M2. Yeah. So yeah, I haven't talked about this, but yeah, you do have maps from the minor relation. Yeah, yeah, thanks.
So T is a minor of both M1 and M2, but it's only a modular, or T is a flat of M1 and M2, but it only is required to be a modular flat of one of them.
Yeah, it's a modular flat of one of them. It doesn't even have to be a flat of the other matroid, actually. Yeah, so it's a pretty general operation. Yeah.
Sorry, I know that this question was already made, but which way go this map?
Yeah,
From where to where?
It goes the way that you need for this to make sense.
From FT to FM1, it's like a product, right?
Right, it's algebra. I just think of this as algebra or space.
So
from F of the minor to the F of the big thing.
Yeah, that's the direction. Okay, yeah. So there's natural maps from this foundation to here and to here. Yeah, and that's how you get this product. Yeah. Yeah.
If T is empty set or like just one edge, is this true? Is this isomorphic?
Yeah. So if T is empty or just has one element, then that's a regular matroid. So its foundation is just a regular partial field, actually. Yeah. Yeah. Okay. Yeah, so this expression that we were hoping is true is not always true. Okay. But basically we showed that it is true in most of the cases that we actually care about. Okay. Okay, so here's probably our most general result from this this project is that if I have two matroids that agree on a common set T, and I require that T is a modular flat of both matroids, I'm adding a condition, then this expression holds. Okay. And yeah, and okay. I guess I won't say much about the proof. I mean, the proof is actually pretty straightforward. It's not like a really deep result. We do this with representations. So we show that for every pasture P, there's an isomorphism between rescaling classes of P representations of this big matroid and P representations of these two small matroids that have to agree on T. And yeah, we show that this isomorphism is functorial with respect to pastures, and then by the universal property of foundations, we just get this result. So I mean, yeah. The point is that we have this. It's a short proof, but it is explicit. It's an explicit isomorphism between P representations of these two types. Okay, yeah. So I want to focus on this corollary actually. So
sorry.
Yeah.
In general situation, do you have at least a map from one somewhere?
Yeah. So in general, there is a map in this direction. Yeah. Yeah.
Can you say something about this map?
Objective or? Oh yeah. Into this, I can't remember what we found, if it has any special properties. Yeah.
It's neither injective nor surjective.
Oh, there you go. Yeah.
That's a special property.
Yeah. Yeah.
But the existence comes from the fact that M1 is a minor of PT M1, M2, and it's.
The existence is just from the definition of this relative tensor product, which exists because T is a minor of M1 and M2.
Yeah, but yeah, we need a map from FM1 to FPT.
Oh yes, yeah.
From the minor.
You're right. M1 is also a minor of the generalized parallel connection, and so is M2. Yeah, you're right. Yeah, we need that. Okay, yeah, so, yeah, so we get this corollary. So this is just a special case, this first one, if T is the empty set, then this shows that the foundation of the direct sum of two matroids is this absolute tensor product of their foundations. So this comes back to Graham's question from earlier, and this is where, I mean, this shows that the tensor product just plays really nicely with direct sum. And actually the same is true for parallel connection. So yeah, and this is because when I have the empty set or just a single element, the foundation is the regular partial field. And this relative tensor product just becomes an absolute tensor product in those cases. Okay. Okay, yeah, so this first one was actually known. This was proved by my three co-authors in a different paper. This one was not known. And yeah, I think it should be pretty important in the future study of matroid foundations. I mean, these are both pretty fundamental operations here. Okay. So I'll just say.
Check that two pastures are not isomorphic.
I would use probably two. By hand.
What does Matroid do?
Yeah. That I'm not sure. I'm not sure about the implementation.
It's a question than like asking a specific morphism is an isomorphism. That's a separate question.
Yeah, let's see. Yeah, I mean, I would guess I think it would be hard to do by hand.
So when you asserted in the previous slide that the two things need not be isomorphic, are you saying that the canonical map is not an isomorphism, or that there is no isomorphism between them?
That there's no isomorphism between the two.
Oh, okay.
Yeah.
How did you check?
Just in Macaulay too, with that.
Structures. I think they have a different number of fundamental elements, which is like solutions to x plus y equals 1. They each have only finitely many such pairs, and in this case, they were different. Okay.
Yeah. Okay. Yeah, so this is what we proved. Okay, so I'll skip a couple slides. This is good. People ask so many questions that I skip some slides in the end. So okay, I'll say a couple things. I mean, okay, yeah, we also worked harder and showed that you can take this parallel connection and actually then delete the common element E and still have this same foundation. This was actually pretty hard. This required some clever ideas from Tianyi, Matt's former student. But the proof idea is the same. We just use representations and find some isomorphism between certain types of representations, and then use the universal property of foundations. Let's see. Yeah, and this gives us some corollaries for example, orientable matroids that, as far as we can tell, weren't known previously. Yes, and this one I really like. So our work shows that if a matroid is not free connected, then its foundation decomposes as a tensor product. And this is just because any matroid that is not free connected breaks down as a direct sum or a two sum, like this. And then by our results, the foundation decomposes as a tensor product. Okay. Yeah, and we also show that this operation, this delta y exchange, preserves the foundation. Okay. And we think this wasn't known for orientable matroids as far as we can tell. Yeah, okay. And it's also not hard to show from this theorem that for any pasture P, if I take an excluded minor for that pasture and do a delta Y exchange, I get another excluded minor. This was known for partial fields, but as far as we can tell, it wasn't known for hyperfields, or of course for pastures in general. Okay. Okay, so I'll just finish with a couple questions for future work. So I think Victoria asked this question already. I mean, when do we have an isomorphism here? In some cases we do, in some cases we don't, as we've seen in this talk. It could be possible to characterize when we have an isomorphism. And I think this would be important for future work with matroid foundations, just because this generalized parallel connection operation is so general. It'd be nice to answer this question. And then one question that I think is really interesting, is there some integer k so that k connectivity guarantees that my matroid foundation does not break apart as a tensor product? Okay. All we know here is that k equals 3 does not suffice. So Nathan Bowler found some spikes, family of spikes, which are 3 connected and have foundations that decompose as a tensor product. So yeah, this could be true with k equals 4. I think we have no idea at the moment, but this seems like a pretty fundamental question, at least to me.
Is that also my colleague too? How do you show that something is in?
Oh yeah, yeah. I guess that's kind of the hard part with this. Yeah, I'm not really sure. Matt and Oliver probably have some ideas though. Yeah.
Do you know there is? No. The question is there a finite integer k? You don't know for sure.
Yeah, we don't know. Yeah, we really have no idea, except it can't be 3. It has to be at least 4. Yeah. Okay. Yeah, and I'll stop there. Here's the paper that I was talking about.
Questions for Zach? Or further questions, I should say.
Do you see any possibility of giving an algebraic proof of the CMOS decomposition theorem for regular matroids using these kind of machinery?
Oh yeah, that's a good question. I haven't thought about it, so I'll just say I don't know, and we could talk about it later. Yeah.
So that first equality, is that just some really elaborate way of checking whether or not T is a flat M1 or a modular flat? Or
this first one here.
Is it? Oh, do you have an example of where this is true and T is not a modular flat?
Yes. Yeah. So if M2 is this graphic matroid of K4, then this is an isomorphism, even if T is not a flat of M1. Yeah. And I should say, I mean, there is a generalization of delta Y exchange called cosegment exchange. We also proved that this is an isomorphism for segment and cosegment exchange. So we do have an infinite family.
I think you mentioned it a little bit in your corollaries, but could you maybe say some more words on like this yoga from going from like I have this result in foundations of matroids to like saying where they're representable?
Oh yeah. Yeah, so let's see. Like this idea here.
Maybe it was the corollary on the next slide. Yeah, like so I guess this orientable result is probably about representations over the sign hyperfield.
Oh, yeah. So basically, yeah, the way we get this with foundations is that if these two matroids are orientable, both of their foundations have a map to the sign hyperfield. And therefore, this tensor product has a map. Yeah.
Thank you.
Are there other kinds of pastures, like pastures that we haven't seen in this talk? Are there examples that are maybe less familiar to us that mean something?
Yeah, I think so. So, okay, I should direct you to this paper called Foundations of Matroids Part 2 by my 3 co-authors. They have a pretty big appendix with all kinds of interesting pastures in there. Yeah.
Is the foundation tutorial on weak maps?
I think probably not, but I can see if my
It's not.
So is this corollary really saying that like giving an orientation of M1 and M2, like there's a bijection between orientations of the two sum or whatever and orientations of M1 and M2?
Yeah. So our proof does give an explicit bijection between, between rescaling classes of orientations. Yeah.
The rescaling part is important though for two sums, because you're deleting an edge, you can't recover anything about the orientation of that edge.
Oh, is decomposing into indecomposables like unique? Yeah, is this?
Yeah, that I'm not sure yet. Yeah, Oliver says yes.
Is there a proof for that?
Yeah.
The fact that F2 tensor F3 is K, and then just insert a bunch of K factors.
Okay. So no.
It's unique up to some. I mean, you can always tensor obviously a factor F plus minus without changing it. And there are some few other occasions where you can tensor with F2, F3, and K. And that's it. Otherwise, it's unique because you decompose a unit group, which is finitely generate abelian group into subgroups. And then if you look at this fundamental elements, X and Y that pair to 1, then your irreducible factors are such that each of such pairs X and Y are contained in the same factor. Then you can just break it down as much. You decompose your unit group into smallest possible subgroups such that for every X, Y that pair to 1, they're contained in the same factor. And when you up to tensor, this is very small.
Any last questions for Zach?
What is the unit group of the tensor product?
Sorry, say that again.
What is the unit group of the tensor product?
You should ask Matt or Oliver. Yeah. Product.
Excellent.
Yeah.
Thanks, Zach.